So hello to everybody. I welcome you to our first webinar this year, which is a starting point of our monthly webinar series, where I would like to explain you all different kinds of X-ray application and interesting things. And today I would like to start with the basic explanation, how does XRF work in the application? So mostly for people of you who are new to that field and just want to know how XRF is working. My name is Rainer Schramm. I'm the CEO of FLUXANA, and I just would like to take you through today. Like always, this webinar is recorded, and so you get a copy at the end. And also there's a possibility to ask questions at the end of this webinar. So let's see. I will explain you what is XRF. We have to look into some physical basics. We have to see how the instrument technology is working. I would like to compare it also to other methods of elemental analysis. How do we calibrate? What kind of sample preparation you have to do? What are the applications where you can find XRF, and of course some examples doing analysis. So XRF means X-ray fluorescence. So there we have two words, first X-ray, then fluorescence. So if we look what is X-ray radiation, then we will see that this radiation is placed in between the ultraviolet radiation and the gamma rays. So it is radiation with quite a high energy, and it's also called ionized radiation. That means it takes from an atom an electron away. So in a certain way, it destroys the atom. And this is what you have to be aware of when you do X-ray fluorescence, that under some circumstances, you can also destroy your sample. The second is the fluorescence. Fluorescence is a phenomenon we know from visual light. And it means if you have a lamp and you send light into, for example, a liquid who shows fluorescence, you see a different light coming out of it. But when you switch off the lamp, it's gone. And if you switch on, it's come back. This is the same for X-ray fluorescence. So it's only appearing as long as the X-ray tube is on. When you switch it off, it's gone. But how does it be created? So the X-rays from your tube make an interaction with the atoms of the elements in your sample. And the inner electrons, so the electrons from the inner shells, they will interact with the radiation, will be taken out, and electrons from higher shells will fill this gap. And now it's depending on how this filling is appearing. That means, for example, if the K shell is filled up by an L shell, we call that interaction K alpha. And if it's coming from a higher shell, it will be K beta. If the L shell has a gap and will be filled, we call it L series. In our spectrum, this looks then like here in this example with iron, so that we have an iron K alpha line and an iron K beta line. So always this pattern comes together. That means K beta is about 5 times lower than K alpha, and this is the case for all elements. If we look to the L lines, I have an example from platinum here. So here you see a pattern of 4 different lines, starting with LL, L alpha, L beta, and L gamma. Yeah, so also this kind of pattern you will find for elements with L lines. If we look in the periodic table, the elements we can create X-ray fluorescence normally are in the range of fluorine to uranium. There are elements like hydrogen and lithium we cannot measure in XRF, but starting with beryllium, there are possibilities. However, you need to have a special instrument, a special installation for that. So that's why typical instrument starts with fluorine. So the first physical parameter we have to look into is the fluorescence yield, which is increasing with increasing atomic number. And I just give you an example. If we look here on these lanthanides, where from lanthan to lutetium, we have an increasing number. If I have a sample where all these elements are in with the same concentration, then you see how the intensity is increasing, because one reason is the fluorescence yield is increasing, so your sensitivity is getting better and better with the increasing atomic number. The second effect we have to look like is the resolution. So if we have 3 different elements, also with increasing atomic number, we will see that, for example, if we look on the L-lines, so like this lanthanum L-alpha, L-beta, that the distance is just increasing with increasing atomic number. That means the resolution is getting better. Another effect we have to look into is how deep we analyze our samples. Yeah, and there is the same effect with increasing atomic number. We look deeper and deeper into the sample. And we can call this penetration depth or exit depth. Yeah, depends on from which point you are looking on this. And in the end, there will be the exciting X-rays which go into the sample, of course, much deeper than the X-ray fluorescence which can come out. Yeah. And also here, I put you an example, a cement, where I just made the order from sodium to zinc, so low atomic number increasing to high atomic number. And here you see then the penetration depth, so how deep I can analyze this sample. And you see for sodium, it's just about 5 micrometer. And for zinc, we are already on 250 micrometers. And now imagine that the particle size is around 50 micrometers. You see that in zinc, we are analyzing about 5 layers of particles, while in sodium, we just touch the particle which is just on the downside. So that's a big difference. So this is why in X-ray fluorescence, everything depends on the atomic number and how good we can analyze an element. Now let's look into the technology. So first we have to look into energy dispersive X-ray fluorescence. There we have an arrangement of the X-ray tube, which irradiates a sample from the downside, and we have a detector just watching the X-ray fluorescence, which are emitted from the sample, and the detector is looking on all X-rays at the same time. There is a different approach here, where we have a polarizer in between the tube and the sample, and this polarizer just modifies the X-rays, in this way we can change the exciting X-rays and therefore optimize the elements we want to see. If we compare both, we can say that the polarization is very good for light matrices like polymers, like oil, like water, like silicates, while the direct excitation energy dispersive XRF is good for heavy elements like metal alloys, for example. The arrangement is mostly like a benchtop instrument or like a handheld instrument. Yeah, you will see this kind of technique. The other possibility we have is in wavelength dispersive XRF. Here, there is a different way to detect the X-rays. That means now we have a crystal together with a collimator and a detector in an arrangement, so that only one single wavelength is taken out of the X-ray fluorescence created in the sample. And this allows us, of course, to get a higher sensitivity and a better resolution. Resolution, you remember, it was good on heavy element side, but not so good for light elements with low atomic numbers. So that's where this wavelength dispersive technique then has its performance. And so this is mostly used to detect main components for light elements, while energy dispersive is very good on the high energy side. In the middle, there's a big field where both techniques just overlap, and depending on the application, one or the other is better or just shows the same performance. Wavelength dispersive instruments you can also find as benchtop design or floor standing design. Both is possible. Okay, let's have a comparison now to other techniques. And there we would compare it to like spike emission spectroscopy or ICP, ICP-MS or atomic absorption. And I just give you now some pros and cons. Just out of the view from XRF, of course, it's not complete. It's just the starting of discussion here. The pro for spike is that you can also analyze light elements, very light elements. You can analyze metals with relatively short measurement times. But the sample must be conductive. That's why non-metals are difficult to analyze. And you always need a calibration which is matrix matched. For ICP, sensitivity is a good advantage. You can go even to ppb range. And of course, also light elements are not an issue. But very often you need to digest your sample. You can only use a small sample amount because of the digestion. And again, you need a matrix matched calibration. In XRF, we have an advantage that often we can work non-destructive with the exceptions I mentioned in the beginning. We have not so many lines than we have in optical emission. It's dedicated for solids or liquids. And here it's more ppm to percent range. And another big advantage is long-term stability. But also we often need to digest our samples. Here we do it into glass. So we make a fusion, a fuse speed. We have limitations in the penetration depth of our samples, like I explained. And again, we need sometimes also to do matrix matched calibrations. But why is XRF long-term stable? While in ICP or XSpike, you very often have to again and again calibrate or adapt your existing calibration. This is because this X-ray fluorescence effect is linked to the inner electrons, while the optical emission spectroscopy is more to the outer electrons. And the outer electrons are much more depending on the chemistry, on the bindings, on the oxidation state, while the inner electrons are quite independent of this. This allows in XRF to describe the whole procedure theoretically, and this works quite well. And as long as we know the instrument constants and all the physical parameters of our elements we would like to analyze, we could establish a so-called standardless calibration. And standardless means in this case that we have to calibrate the instrument constants, but for the application or for different samples, we don't need then really matrix match standards. Yeah? So this is possible because we could describe very well the whole XRF process. But what does it mean, a standardless calibration? It would mean that we also need an ideal sample so that the sample itself is not a problem. And this means the sample should be homogeneous with a known density. It should have an ideal surface. It should have a defined sample size, and we have to know the mass. And mostly we will find this as metals or as fuse speeds or liquid. Fuse speed means here that we have a powder, and the powder was dissolved into glass to make an ideal sample. And in an ideal sample, this means that the layer we analyze, or the volume we can say we analyze, is representative to the rest of the sample. This is important because we have learned that for some elements our penetration is very little. So only when the whole sample is homogeneous and the analyzed layer will really represent the whole sample, we can do a real good analysis. But what means when these conditions are not fulfilled? We have to do an empiric calibration, which means we need standards. And then non-ideal means like very often for press pellets or loose powders. Because in this case, like you can see in this schemata, in a loose powder, the density is quite undefined. We have holes in between, and the volume we analyze is not really filled 100% by sample material. If we look on the pressed powder, you see that there are particles, and the particles, they have a margin, and at these particles, the X-rays are scattered, and we lose information. So this is why it is not an ideal sample for us. That means samples could be considered as heterogeneous. Another problem will be if we measure, for example, with a handheld on a curved surface. This is not ideal. Or our sample is too small that it doesn't cover really the X-ray beam. So what kind of sample preparation do we use in XRF? So mostly we have just a powder we would like to analyze. So we can just put it into a sample cup, which is also used for liquids. These cups are just covered with a film at the bottom. The film must be transparent for X-rays, and then we irradiate the sample from the downside. The powder could be also pressed together with a binder so that we have a pressed powder pellet, and then this pellet is analyzed, or the powder is really digested into a glass. Then we have an ideal sample, and so because also here the surface is given by the platinum mold. Other ideal samples would be metals, so they can be just measured like they are. Or we have, for example, a polymer which could be pressed into a hot press to get also a kind of a disc so that we can analyze it directly. If we look on the applications, you will see a long list of industrial applications where XRF can be used. And this is mainly to inorganic analysis. That means, remember, the elements from fluorine down to uranium. When we want to see that into materials, this opens a lot of possibilities, because in the end, X-ray fluorescence is just an atom counter. That means we count how many atoms of an element are in a material. And this is, of course, a wide range of different materials where we could do that. Organics, however, cannot be analyzed. So whenever we talk about molecules, this is out of our scope. Just inorganic elements, so from fluorine down to uranium. Now I would like to give you some examples how we can use this. So if we just want to have a survey of a material, we use a standardless calibration, which mostly comes with an instrument, but then we need an ideal sample. And a good example is glass, just a window glass we would like to analyze. And then we can do a direct measurement. We don't need a sample preparation. All elements can be measured, and except of oxygen, but oxygen is linked stoichiometric to the element. So that in this way we can also calculate it. And if we then look on an example like this DGG1 standard, you see that between the given value, the specification, and the measured value, we have quite a good agreement. And remember, this is a standardless calibration. That means this kind of sample material was never in the calibration. It's just this theoretical relationship is described, and the instrument itself was calibrated for the sensitivity. And this is good enough to do such an analysis. But what happens if we use such a standardless calibration approach for a non-ideal sample? And this would be, for example, a cement prepared as pressed pellet. Remember, pressed pellet, we said we have a lot of particles, there is scattering inside, and we lose information. And in this special case, if you just analyze this pressed pellet, you will get a sum concentration of all elements in the range of 80%. So 20% of information is just lost. So to use that still to do quantitative analysis, you could do a trick that you say, okay, but I know all elements, and so I can normalize this to 100%, and then you would get quite a reasonable result, but only if this is allowed to do. And here you see, for example, the comparison between the certified value and the analyzed value. So there also you see quite a good agreement. However, if you have compounds like here loss on ignition, which is a kind of carbonates and moisture which is in that sample, this is ignored. Yeah, so this means this concentration is just added to other elements which are then analyzed too high. So this is the disadvantage of this method and using the standardless approach for a non-ideal sample. But then other application field is that we just do a QA and we have a calibration based on certified reference materials and we use an ideal sample. This would say we make really precise and high accurate analysis. For example, these cements prepared as fused speed. So the powder was dissolved into glass, dilution 1/8, with a perfect surface as the negative of our platinum dish, and the sum of all measuring elements as 100%. Of course, oxygen is calculated by the stoichiometric ratio. And then, first of all, you see that the reproducibility, the precision is very high. That means this sample preparation gives us only a very little error. And the comparison to the certified value also gives a good agreement. And it's of course depending on what standards are used to calibrate this. Another example, if we make a QA with a non-ideal sample, and here I just use, for example, car catalysts prepared as loose powder. So we just put the powder into a sample cup. So we have here this situation, and then we measure it. And here the interest is mostly only on the precious metals you will find in that material. And why does this work so well? It is because our elements of interest have a high atomic number with a very high penetration depth. So the whole cup is mostly analyzed. And the fluorescence yield of these elements is very high. So we have a high sensitivity. So we can even go down to traces here. And of course, we calibrated this application by CRMs. So, and the CRMs were prepared in the same way than the samples. And there's a general rule that means as higher your atomic number, as more it's possible to use press pellets, loose powders, because of this effect. And as lower is your atomic number, you are looking on light elements, then it becomes more and more difficult to do press pellet loose powder for these elements because the error is increasing a lot. And all these problems starts with penetration of fluorescence yield and so on. So then here another example, raw material analysis, also empirically. So let's say we have sulfide ores and we would really want to do a good analysis, high precision, high accuracy. Then we will do a calibration really based on certified reference materials. We will add some chemistry to get rid of the sulfide, which would destroy our platinum ware in this case. And so if we have this all under control, we can do very good analysis. Again, because we use fused speed, we have a good precision. And this allows us even to analyze such difficult materials. And you see as an example, I have here copper sulfide or lead sulfide or cobalt sulfide as example of high precision and accurate analysis. So let's summarize. XRF, we can say, is a robust method, long-term stable. It only little depends on element chemistry, and this gives us the possibility to use such standardless calibration approach that we can really describe the whole process even theoretically. The strength lies definitely in major and minor components, not so much in trace analysis. Solids are mostly preferred as sample materials. We have a very good traceability if we have ideal samples like our fused speeds. That means you could easily also create secondary standards and make your own calibrations when there are no CRMs available. And this is a very large area of application, and it's very powerful if, of course, you use the right sample preparation. And like always, there should be some experience involved. And if not, then you are always welcome to contact us and to help you to setting up your application or to answer your questions. And this is the end of my webinar. And at this point, I thank you for listening. And now I will have a look on all these questions which are already here in the list. Let me see. There is one question: how do I know the detection limit of each element? You could use here the classical approach. That means you measure a sample and you just measure the sample 10 times. And then you calculate the standard deviation for every element, and the standard deviation multiplied by 3, this would be your detection limit. Yeah, this is a first approach. Of course, as closer this result is to the real detection limit, as more precise is it, but this is a good starting point. Then what would be the plastic sample preparation procedure for plastic samples? Plastic has the disadvantage that if you put it in a grinder, that it starts to smear. If it's getting hot, it starts to melt. So probably you need to use liquid nitrogen to make it brittle so that you are able to grind it down. Then you can make a classical press pellet. Or if you can melt it, a hot press would be even better. Yeah, that would be the sample preparation I would recommend. Then someone asked about LL lines. He knows L alpha and L beta lines. Okay, LL lines is also part of the element of the line table. So if you go to a physical line table, you will find there for every element these kind of lines. Just have a look there. Another question, if you someone wants to get the presentation, yes, of course, we can send you the presentation after that. Also, someone else asked for the recording. Yes, you will get this also after the webinar. There's another question. Is it advisable to prepare a calibration for few speeds with proper calibration standard, or is it just for press pellets? When you do a real dedicated application where your standards are prepared in the same way than your unknowns, it always will give you the best result. Sometimes you can use also a standardless software and only your preparation is like an ideal sample, like few speeds. If you don't add any chemicals and it's just a straightforward preparation, let me say 1 part sample, 8 part glass former, glass like lithium tetraborate, then it will also work with a standardless approach. But of course, a dedicated application is the same or better quality. So let's see what else comes up. Someone asked why in this auto catalyst, in this car catalyst, we measure cerium. There is indeed cerium inside, so it's not CO2. It consists of a zeolite, which is of course silicon oxide and aluminum oxide. There's zirconium oxide inside and cerium oxide as well. Yeah, definitely. And you're right, it's CEO2. Oh yeah, this is an error. Okay, thank you very much. Do you have raw material standards for analyzing heavy metals? Perhaps there you should have a look in our FLUXsearch database and just make an element filter on it so that you can really see if you can find something which fits to your application. Yeah, there are about 16,000 different materials, so I think you should be lucky there. For cements, standardless methods versus calibrated methods, how much difference we get? Well, this depends how good the standardless methods was created. I would say in an ideal case, there is no difference. But of course, in the real world, a calibrated method is always better because it's more standard matched and it's really fresh standards prepared and it's probably better. Yeah. Then there is another question. What is the maximum kilovolts, the voltage, needed to emit electrons from all elements in the periodic table? This is a very good question. You always have to adapt your excitation voltage to the elements you would like to analyze. And if you want to have a real physical answer, you have to go into the table, and for every element, you will find an absorption edge, and this is really the minimum energy, minimum voltage you need to excite that element, and this is a bit increasing like the atomic number is increasing. So there is not one answer for this question. You really have to get the answer for every element. Then for press pellet calibration, how similar should the particle size be in the calibration standards in the real samples? The same. It must be the same, because all theoretical approach and all calibrations cannot take into account the particle size. So further question. Let me see, for creating calibration method, how many samples and what kind of standard samples have to be used? So first of all, the standard samples have to be matched to your samples. Yeah? So you need a matrix match. The second is that the number of samples, I would say if I make a calibration curve, I would like to have at least about 5 points. I think that is a good starting point. And then you need more standards if you have a lot of inter-element effects. So if you have disturbing elements, which makes your lines curved, then you need, for every of this disturbance, you need an additional standard sample which represents this effect. Yeah, so it's 5 plus. Is it possible to analyze opaque liquids such as oils or tar? Yes, mineral oils are analyzed, for example, to analyze the sulfur or to analyze the heavy metals in there, like we know it in oils we put in the car engine, or it is used for used oils coming from engines to see the wear. And the same for tar, also this is possible. Tar, it's a bit difficult to preparate. You have to warm up it first, perhaps to pour it into a sample cup, then let it cool down, and then you can analyze it. Yeah, so this would be the way to do it. I think I don't see any more questions. If you have more questions, feel free to send it by email. I'm always happy to answer these. And I really have to thank you for all these nice questions and for being here into that webinar. And I hope you will come back for our next webinar next month. Thank you very much. I wish you a nice day, and bye-bye.